us now look at how we can apply a camera sensor for our automotive applications to see if it can be we can use this sensor for building an IoT application. Okay. As you know, two hot topics exist today in the world of automobiles, IoT and automobiles. One is in the area related to electric vehicles, how IoT can assist the use of electric vehicles and what kind of technology can IoT offer is one question. The second question is about autonomous driving, right. So, very hot topic. So many courses are there on application of artificial intelligence and machine learning for automobile applications and autonomous driving and all that. So, it is a hot area. We can't obviously, our focus is really not there. Our focus is more on a very narrow part of all what we are talking. One thing is, if you want to do any one of those, you want to build any one of those applications, you must know some real basics. And what we will try and do is to cover those basics, including your own ability to experiment in at least a simulation environment. Okay, that is the key. That is what we want to achieve. So, let us take the example of a camera sensor. Now, camera sensor obviously gives you an image. Okay. Apply this image and a series of images which make a video at a particular rate. When images change at a particular rate, you get a video stream. See whether this image can be used to detect important things when a vehicle is moving in on a road. Okay. Now, this itself is a hard problem. First of all, if you take Indian conditions, how do you define what a road is? Often if you go to the slightly rural and village side, there is no road at all. Now, what is a road, what is not a road is difficult to even identify, right. So, that is one part of the story. Assuming that you are not there, you are in a urban situation, you are in a large city or at least in a reasonable city where there is a lot of traffic out there. There are roads and there is a tar road or a concrete road, there is a road and then there is a road divider and all of that. So, let me point you to this picture which is here. You have the road edge on the left, you have the road edge on the right which is here. Okay, let me take another. So, this is the road edge on the right, this is the road edge on the left and this is the road divider, perhaps a big monster in the middle which is trying to sort of ensure that traffic moves in a disciplined manner. If this is not there, it can be chaotic because traffic coming in opposite direction can actually come into this space and in this direction, traffic in this direction and create a complete jam. So, they put a traffic divider. Not only that, there are also lane separators, right. There is a line, typically a line which sort of line markings which actually say that this is a lane and this is another lane. So, you have lane 1 and you have lane 2. Typically one of the lanes should be a fast lane, the other should be something for moving at a constant speed. So, things like that, but often you know vehicles just go on either side without really worrying so much about what is a fast lane and so on. Now, if you look at this picture, look at this point here, okay, this all that is happening here. Here you will see that this is a line, all right, which is something that you want to detect. Ultimately, you want to detect this line, right. If you detect this line, if you detect these lines, this is, let me call it line 1, line 1, I will call this line 2, this is line 3 in a way, this one, and this is line 4. There are 4 lines. How do you use a camera sensor and what kind of image processing tools are required to do this image processing to detect this line. See, you have to note one important point. This is something that should be derived from an image. Okay. What will you see in an image? Typically if a camera is kept outside the windshield, it is not seeing this nice picture anymore. It is seeing vehicles, it is seeing vehicles in this direction, it is seeing its own vehicle, it is seeing some vehicles in the positive direction, it is seeing trees. I just draw some things, and then it is seeing people, right, it is seeing people walking, it is seeing cyclists, it is seeing vehicles moving on either direction, also in its own direction. So, if you put a camera sensor here, let us say you put a camera sensor here, okay, and assuming that it has a good field of view, I will put it somewhere here so that you get a feel, okay. You get a good field of view. This is the camera sensor, is getting a good field of view. You are seeing all of this, which means you have to break down this image into segments and perform a segmentation of the image. You want to do segmentation of this image and only detect I will remove all this, right, I will remove all this and detect only this you want to detect. Now you see it is not so easy already. If you want to get this beautiful picture, it is not easy. And why do you want to get only this? That is your next question, right. Why am I interested in this? You are interested in this because you want to ensure, let us say you are the car, you want to ensure that you are always moving in a straight line, right. Unless you know where your left edge is and where your right edge is, you are not going to remain straight, right. Remember the other algorithm that we showed, a simple algorithm where there is a sensor and there is an actuator. Let us assume that in this case, in this particular example, camera is our sensor and actuator is indeed the steering wheel. If you want to remain straight, your camera sensor should keep telling you where your left edge is, where is your right edge, in which lane you are and in what direction you proceed. Supposing the road curves like this, right, then you will come here and then this sensor will give a command to the steering sensor that it should turn also to the left so that it continues to remain in a straight line as much as possible, right. That is the only way by which. So, your goal should be to ensure that you are always in a straight line, which means this edge and this edge you have to detect accurately, okay. So, that is what our whole exercise in this course is, how to get to this edge as accurately as possible and how to detect these lines. I have been using these words. So, if you want to get this line, you have to do two things. A, you have to do edge detection, and after you do edge detection you have to do line detection. You have to do edge detection and then line detection. A has to be done first, then you follow it up with B, A leading to B, edge detection leading to line detection, then you will get this line perfectly in order. Now, so right, so I have motivated you well enough. Here the trouble is, if you look at this section, okay, edge detection, this one is a rich area of research by itself. It is a rich area, extremely rich area, and there have been developments over the last 50 years. 50 years of development. Okay. Therefore, it is hard, this edge detection is an extremely hard problem, and people are all the time after this, because if you can do this edge detection accurately and you can do line detection, then many problems in autonomous driving are actually solved, right. Therefore, several algorithms are available for edge detection. Out of so many of these algorithms, you may want to choose one candidate algorithm which is of interest to you. Candidate algorithm for edge detection. Now you may ask, how do you choose what is a good edge detection algorithm itself? Obviously, when you say it is a good edge detector, it should do good edge detection. Obviously, what does it mean? It should minimize false positives and false negatives, very important. So, if you say candidate, one of the requirements A is this. Okay, what is B? B is good localization. Good localization. What does it mean? It simply means that if this is the edge, let me take another color, okay. If this is the edge, it should not give me an edge which is here. It should not give me an edge here. It should not give me an edge here. If it gives me an edge here, you can now imagine how disastrous it can be. The vehicle gives me an edge which is here or maybe a little here, is disastrous. This is actually beyond this good road edge. You do not know what is there. It could be a ditch, it could be simple mud, untarred part of the road, there can be trees, right, there can be trees, all this, or it can be anything. So, unless you have extremely good localization, you are not going to, you are going to have a problem, right. So, I will put back this edge. So, it should have good localization, and it should just indicate one single point, okay, just one edge it should indicate. It should not indicate for every point here, for every point, let me take another color, for every point here, it should not tell me that there are multiple edges. They should not show me multiple edges. This is not acceptable. It should always say that there is only one edge for a single point. This is also another important thing. Okay. So, this is what you should be looking at. Now, the question is, what is this candidate algorithm? What is this candidate edge detector? Well, there are several books and several papers and several algorithms on this one topic. I found a good book, okay, which I am sure you will be able to download, on computer vision. So, I will write it here, computer vision. I think it is called Fundamentals of Computer Vision by Mubarak Shah, SHAH, Professor Mubarak Shah. I think it is called Fundamentals of Computer Vision. Please have a look. If you Google for this, you will find this book, and I would strongly recommend you to read the chapter on edge detection. Edge detection chapter. Okay, you must do this. So, and this is not a full course on edge detection. I am just trying to motivate you towards our IoT examples. So, therefore, you must spend sufficient amount of time understanding the candidate edge detector, and the candidate edge detector most popularly used today is canny edge detector. Okay, so I will put it here, canny edge detector. Okay, so if you look at what the main purpose behind an edge detection is, if there are any abrupt changes, any abrupt change is essentially an edge, isn't it? Any abrupt change is indeed a edge. Any sudden change in image. See, till here it was one type, suddenly you have a change, and therefore there is, it indeed is a candidate edge. So, any sudden change or discontinuation in an image or discontinuity in an image is essentially, you can declare it as an edge. It is a very simple definition, but then if you read that book by Professor Mubarak Shah, and he himself will explain that when you talk about edges, you talk about surface normal discontinuity, depth discontinuity, surface color discontinuity, and illumination discontinuity. All of this can potentially create edges. Okay, and there are so how do you measure which is a good edge detector? How do you, what is there a metric? Is there a metric to say that this is a good edge detector or this is not so good and all that? So, there are two terms associated with edge detector, one is called precision and the other is called recall. Okay, all edge detectors are essentially measured using these two, what is the precision of the edge detector and what is the recall of the edge detector. And you can have a step kind of edge detector, you can have a ramp kind of edge, you can have a roof kind of edge, you can have a spike kind of edge. So, all these type of edges can exist in a this is a roof in an image. Okay, so again I have picked most of it from Mubarak Shah's book. So, if you read that book or look at his notes on the web, you will find all of this. So, it is extremely useful and quite intuitive for you to understand. So, essentially he writes, he shows a nice picture and he explains that you think of all this is darkened. Okay, this complete thing is darkened. In fact, I will, what I will do is, just to save time, I will make a very small one. Okay. And just darken everything here, and you can draw a line here like this. You could draw a line. What does it mean? It means it is all bright here. If you go in this direction, you can do, image is essentially two dimensional, right? You go x and you can go y. So, if you go in this direction, it is all bright, suddenly it goes black, it goes dark, then again it rises back, right. So, essentially you will get a signal like this, you will get a signal like this. This image, this is an image where there is a dark patch and there are two light patches on either side. So, this is light and this is a dark, you will get something like this. Now one simple mathematical way to detect that there is an edge is to differentiate this. You take the first derivative, you take the derivative. So all edge detections will essentially lead you to taking the derivative. If you take the derivative, you will get a something like this, you will get, right. So start using this derivative both in the x direction as well as y direction, and then detect edges nicely. Okay. However, any image if you take any image, it is not easy to process the image directly. First of all, there will be a lot of noise in the image, there will be a lot of noise in the image. So you have to remove the noise, and typically what they do is, so you essentially okay, let me do something peculiar to this image so that you get a feel for it. Essentially when you say noise, no, the noise can be superimposed like this, okay. The noise is getting superimposed on this edge, and it is not letting you detect it properly at all, goes up down and all that. So one thing what you can do is, again think intuitively, what can you do if you have a system like this? Make this line a little thick, make it thick, that is all. But you may now ask, if you make it thick, won't it look blur? Yes, it will look blur, this will lead to a blur, that is right. Let it be blur, but at least you have smoothened it, and after blurring you still have a beautiful edge which you can detect. Therefore what people normally do is, particularly if you look at Canny, I am not going into details of all types of edge detectors, you apply the before you do any first derivative or anything, before you apply the derivative, you essentially you take an image, take the image is your input, right. I will input image, 2 dimensional, please note, x and y, 2D image, and you apply a Gaussian filter. Typically they choose a 5 cross 5 Gaussian filter. Very simple, you take neighborhood pixels of 5 cross 5 and substitute every pixel with the average, that is how you get this. You take 5 cross 5 here, apply a 5 cross 5, you will get an average number, replace each one of these pixels with that average, and then go on doing it, you will get this blurred image, and therefore you get a smoothened. So when you say Gaussian filter, this is mainly for smoothening. So remember, first step is smoothening. After this, so this is input, right, this is input, and here is your step A. Let us come to step B. Step B is applying what is known as a filter. I am just talking of Canny, please note, I am only talking of Canny edge. By the way, this smoothening is common to all type of filters, so really you do not have to, there is nothing special about it. The Canny edge is special because it does several interesting things. So let us see, smoothening is done, then the next step is what is known as a filtering. Essentially when you say filtering, what you are interested in is finding the intensity, gradient finding the intensity gradient of the image, right. This filtering also includes getting to the first derivative, okay, that is important. Filtering plus first derivative, you have to do both. Then essentially when you are saying first derivative, you are saying d by dx of the image I and d by dy of the image, which essentially leads you to generating a vector. Essentially you are generating a vector which has magnitude components and the angle component. Essentially you have the magnitude and you have the angle. So, angle is theta. Magnitude, essentially what is all this, what are we saying? You are saying how much is the change in intensity. You have to quantify this, right. So, typically edge gradients, essentially you are trying to get to the intensity gradient, and this edge gradient essentially is G, is computed in a very simple fashion, Gx square plus Gy square, okay. You know what Gx and Gy are. This is the horizontal gradient and this is the vertical gradient. Since we said gradient, since we said it is a vector that we get, this theta is quite simple. This is nothing but tan inverse of Gy by Gx. So, now this is all you have to do in Canny Edge. All of this is done by one single function in OpenCV. However, you must know it properly, right. So, that is the reason I am trying to explain this. Anytime you have an edge, the gradient is always perpendicular to it. Gradient is always, so this is very important, this is 90 degrees, right. Now on this gradient you apply a simple a threshold. You apply a threshold. I will show you with an example. Again, you could find them in several books. I will show you a very simple example by sketch it and show you, so that if you take this system, you now know there are 1, 2, 3, 4 edges, right. Now consider this edge, consider this edge. The gradient is always perpendicular to the edge, we already said this. There is a pixel point here, there is a pixel point here and there is a pixel point here. Let us call this C, let us call this A and let us call this B. You know now that it is very important that you have 3 points and you do not know where the edge is. Why? Because this is the gradient direction. In this gradient direction there are these 3 points and you really do not know which essentially is the pixel that you have to worry about, which means C and B have to be suppressed. Obviously the gradient, while the direction of the gradient is perpendicular, it is maximum at this point, maximum, right. So, the next step in canny edge is suppression of non maximum, maximum suppression. Okay. So, then if you suppress these two, you are only left with, essentially you are left only with this A, and that indeed is the point of interest, pixel of interest, edge of interest, and you have to now say, yeah, this is the point I wanted to pick, and you do this, and then you find out essentially that the edge has been found at this point. Okay. So, you have to do this all along, you have to do it across the complete image, and then you have to essentially ensure that you have detected the edge correctly. This is not over, the problem is not solved, because you may get another very close point here, okay, which is also along the same gradient. Far away points no problem, what about nearby, right, that can create another mess for you, which means you have to apply thresholding correctly, which means you normally do what is known as two level thresholding, which is called high and low thresholding. Okay. Unless you apply this 2 level thresholding, you will not be able to get rid of those which are extremely close to the edge pixel at all. For that, you can look at, again, several examples exist. I picked one from explanation related to the canny edge. Here this is the high, and this is, let us say this is low threshold, and this is high threshold. Now look at this picture. Okay. The idea is pretty straightforward. If you apply a single threshold, supposing you apply this threshold, okay, what will you get as an edge? You will only get this part, and perhaps you will get this part, which is not true. You have lost this part, you have lost this part, and you have also lost this anyway. You do not mind losing this because it is really not an edge, whereas this is a continuous edge. So, what you do is you, and obviously if you have points here, they will never even show up. If there is an edge here, it will never even show up, so that is okay. Now, how to differentiate between this system and this? So, it is like this, between this edge and this, how do you ensure that you pick this but not this? In algorithm form, it is quite straightforward. Take a what shall I say, pixel, take a pixel here which is called the edge pixel, take a single edge pixel, okay, and then start looking at it, start following it. If it continues to be part of the line, part of this line, then continue to consider it as part of the edge, okay. Keep following it, but remember, you will have to start with a single pixel which is above the high threshold. If there is a pixel above the high threshold, keep following it and then trace it through. So, automatically this will come through, this edge will come through, but B will not, because it is below the high threshold. in this manner one could actually detect the fact that A, as they call, is essentially a sure edge, is actually a it is a sure edge, right, because it is above the high threshold, and C, this point C is actually below the high threshold, but as you are following, or nothing but as it is connected, you can say it is connected. You are following meaning you are connected, because C is connected, you essentially declare it part of the edge, and anything else is simply discarded. So, this question will be, how do you choose the high threshold and low threshold, and that is something that you could really experiment with when you start coding for using canny edge detection system. So, let me summarize the whole process of canny edge, so that you will be able to experiment with canny edge successfully in any code that is given to you, right. First step is you need to do a, so you take the image as input, then what you do, apply blur, I will simply say Gaussian blur, apply a Gaussian blur. Once you do this, then you would find the compute the derivative, okay, of the, I mentioned to you about the filter step, filtering, right, filtered image, compute the derivative of the filtered image. This is typically a Sobel filter in canny edge, okay. Then find magnitude, and orientation, theta, right, theta you have to find, of the gradient. Then what you do, apply non maximum suppression, then apply hysteresis threshold by looking at high, low, look at connected pixels. This completes the whole operation of canny edge. Next important step is trying to find the line, and for this we will have to look at another important algorithm, and that algorithm indeed is the Hough transform. So, one way of sort of blurring this edge is to do an averaging, as I mentioned, but in canny edge what they do is they take a Gaussian blur. So, this blur actually is Gaussian blur, and so you take the original image, do a Gaussian blur, apply the Sobel filter, then do non maximum suppression, and then follow it up with this hysteresis thresholding, 2 level hysteresis thresholding. So, let me quickly come back, Gaussian blur, then complete the derivative of the filter, and apply the Sobel filter. With Sobel filter, find magnitude and orientation theta of the gradient, apply the non maximum suppression, apply hysteresis threshold, and then you do half line transform.